Welcome to the tutorial on kinetic and potential energy. We'll be exploring the two ideas, the math formulas for each one, and how they relate to each other. Also, these do go along with your Cornell notes, although they might not be in the exact order. The basic information should be covered, and you can use this tutorial to help you fill in and or review for tests. Hey, we're going to start with kinetic energy. Kinetic energy is basically energy of motion. So, kinetic energy, energy of motion. Now we can calculate kinetic energy just using a formula. Try zooming in here. So, formula for kinetic energy. We can calculate kinetic energy basically by taking the mass times the velocity and squaring the velocity, and after you do that, divide everything in half. Oops. Divide everything in half by dividing by 2. Okay. The important thing to remember here is it's really important that you square the velocity first following the order of operations, then multiply by the mass, and then divide by 2. So let's just make up a scenario here. Let's say we have, well, we can use our train, but we'll pretend it's a toy train so we don't have such big, huge velocities and masses. Let's take our train here and let's make up some numbers here. Let's say the mass of our train is, oh, I don't know, how about 100 kilograms. So that would be the mass. And let's say the velocity of our train is equal to, I don't know, how about it's barely moving. Let's make it go really barely at all. 5 meters per second. Now let's use that to calculate kinetic energy, how much energy it has. So we're going to use the formula here. If you have a formula box, you can use that. I'm not going to make it quite so formal here. I already have the formula box. So actually next thing I do is I list my variables out and see what I have. So let's do that actually. Kinetic energy. We don't know what kinetic energy is. That's what we're going to figure out. Let's see here. Mass, we said 100 kilograms. And velocity, we said 5 meters per second. Now, let's use the formula there to solve that. So, to show our work, and this is the part that takes the most getting used to here because you have the squared unit. So it's really important that you keep track of parentheses and stuff like that. So let me box this other stuff in. Alright, let's show our work. So what we're going to do is we're going to say, okay, kinetic energy is equal to the mass of 100 kilograms multiplied by the velocity of 5 meters per second squared, and we're going to square that, 5 meters per second, and then we're going to divide everything in half. So the next thing I'm going to want to show is, let me switch colors too. Next thing we want to show is squaring that number. So what we're going to do is I'm going to rewrite my 100 kilograms and then I'm going to square my 5. So 5 squared is 25. Now, the squared, I just squared the number. Now I have to square each unit. Okay, and here you want to make sure you write everything, the squared small now. So now it's meters, and the squared belongs to the meter now. And seconds squared. Okay, so we've taken care of our units now by squaring everything. And then we're going to divide all that by 2. Now, you can do the next step in one step if you'd like to. 25 times 100 is equal to a 2 and a 5, and then we got 2 zeros there, so 2500. Now, what are our units? We have kilograms multiplied by meter squared divided by second squared. So I'm going to just copy that down. Kilogram times meter squared per second squared, and then I got to divide that all by 2. So 2500 divided by 2 is equal to 1,250, and again my units are kilograms times meter squared per second squared, and it turns out that that is equivalent to another unit you already know. Any guesses? How about 1,250 joules? So a kilogram times meter squared per second squared is the same thing as a joule, and so we just write it as a joule. So that's how we calculate kinetic energy. Make sure you take your time on those, make sure you show each step, and you're careful to do that. Okay, potential energy can basically come in two different forms. It's basically stored energy, so if you're on your notes, looking at your notes, potential energy is a stored energy. And it can usually be stored because of one of two reasons. It's stored because of its position or its shape. So for example, if I take this ball, I move it up a hill, it has potential in it to roll down. And so we would say it's stored energy because of its shape. Because of its position above the bottom of the ground. Bow and arrow is an example of storing energy. If I pull this back, I can store energy. And if I let it go, that will get converted into kinetic energy. So again, I'm storing energy because of shape in this case. So that's what potential energy is. Now, I sort of hinted to it, but there really are two forms of potential energy. One form we call elastic, and the other form we call gravitational. And gravitational is obviously stored energy because it's some height above the ground. And there are some math problems we can do for that, and I'll do some with you on my next screen. Okay? Elastic is pretty straightforward. Imagine a spring, a rubber band, a bow and arrow. Anything like that is storing energy because of its elasticity. And so no math problems with elastic potential energy, just the knowledge that it exists and that we can actually store energy that way. Okay, on to the math problems for gravitational potential energy. Next screen. All right, we can actually calculate how much potential energy or gravitational potential energy something has just based on two things. So we could figure out, for example, how much potential energy does this person have walking across, this is called slacklining, by the way, slacklining across these two rocks here. In other words, if I took the person and lifted them up from here to here, I'm storing energy in them. How much energy am I storing in that person? Well, let's figure that out. First of all, the formula to calculate this would be gravitational potential energy is equal to basically the weight of the person multiplied by the height. If I don't ever give you weight directly, you can calculate weight if you know, I think I'll just leave it at that. So the weight times the height. So if I zoom back out here, how would I figure out their weight? Well, I would just simply you could use a spring scale. So let's say I hung this person from a spring scale. I could read the number off my spring scale, and it would tell me how many newtons of weight is pulling down on that person. And so let's just assume that there is 600 newtons of weight pulling down on that person. So now I need to know their height above the ground. So now I know the weight. How do I figure out the height above the ground? Well, I'd have to measure it somehow. So if I got a bunch of meter sticks here, and I measured their distance from here down to the ground, this would be their height. And let's just say their height above the ground is equal to, I don't know, how about 100 meters. Now I have everything I need to know to calculate their potential energy. So let's go ahead and do that. Zoom in just a little bit here. So how do I show my work for this? I would say GPE is now equal to their weight, which I said was, what did I say it was? 600 newtons. Try to keep it visible there. 600 newtons multiplied by their height, which I said was 100 meters. And that gives me their GPE. So I multiplied 600 times 100, and I'd get 6 with 4 zeros after it. 60,000 Newton meters. And a Newton meter, as we've already learned, is equivalent to a joule. So this person, just because of where they're at, has 60,000 joules of energy, potential energy, stored in them. In other words, if they fell and there was no friction from the air, you could actually convert that into kinetic energy, and just before they hit the ground, they'd have 60,000 joules of kinetic energy. Okay, so we can actually convert from potential to kinetic. Hey, mechanical energy is basically when you add both the potential energy in an object plus the kinetic energy in an object. And it would be important to know before you do a problem like this, are we going to include friction or are we going to ignore friction? And in your first tutorial, we are going to ignore friction. So not exactly perfectly real world when we ignore friction, but it will help clarify the concept, and then later on I'll tell you how it works when we include friction. So to illustrate this, let's say we have a pendulum, and I put a 1, 2, and 3 because those are the positions in order. So let's say I pull the pendulum up and I'm just holding it right here, position number 1. We need to figure out how much potential energy it has, how much kinetic energy it has, and how much mechanical energy it has. So, potential energy. All we need to know to calculate the potential energy is the height that is above the ground. And just for the sake of clarification here, let's just say that the ground is basically right at position 3 there. So the pendulum, once it swings down, it won't touch the ground, but it would be just barely above it. Okay? So the pendulum is being held up right here. How much potential energy does it have? Well, if I gave you some numbers, you could actually calculate it. The height above the ground and the weight of the pendulum would give you its potential energy. So let's say, just for the sake of illustration, it has 10 joules of potential energy. Okay. Is it moving yet? Well, I'm holding it here. So it has 0 kinetic energy. Alright, so what is the mechanical energy? You just add those two together and you would get 10 joules. So the total energy stored or inherent in that ball or in the pendulum right now is 10 joules of mechanical energy. Alright, what about halfway down in its fall? So you let go, pendulum starts to fall. About halfway down right here. How much potential energy do you think it has? How much kinetic? Okay, well, let's take a look at that. Well, the height above the ground here, even though it's moving, it still has potential energy because it's above the ground. Okay, so it's potential energy about halfway between my fall there. So just guessing, I would say probably has 5 joules of potential energy. Well, what happened to the other 5 original joules of energy the ball had? Well, it got converted. It got converted on its fall into kinetic energy. So if we ignore friction, we would know it has 5 joules of kinetic energy. And you can see that the ball did not lose any mechanical energy at all. It still has the same amount of mechanical energy. Now, it's still going, okay? It's still falling, and it's right here. Now, if we kept it going, it would spring up this way over here. But let's imagine that we take a snapshot in time of when it's right here. Well, it's not really above the ground at all anymore, so it actually has 0 joules of potential energy. And you probably guessed right, all that potential energy would be converted to kinetic energy, and so I still have a total of 10 joules of energy. Now, if we think about what would happen next if I let the ball continue to swing up this way, well, that potential energy that kinetic energy that it has right now would get stored back into kinetic energy, and the ball would actually go to its original height, just on the other side. Oops, H-I-G-H-T, original height. Okay, and therefore the pendulum would swing forever in our scenario here, but that's because, again, we chose to ignore friction. Another tutorial later on, I'll tell you exactly how this works when we choose not to ignore friction and calculate the mechanical energy. And that will explain why a pendulum actually does come to a stop.